Okay, now we will look the same things actually, but uh, our model is not in parallel plates. We are in circular pipe. So this is actually proposed by the Poiseuille. So we call it as a Poiseuille flow. So previously it's about the Couette flow. So it is a flow between two parallel plates. Okay, so that means the plate is in rectangular shape. So now we are do the same things, the same idea, but the shape is in circular. So means that we need to use the idea of polar coordinates. So this is the flow in conduit shear stress distribution across a pipe section. The velocity distribution in a pipe is directly linked to the shear stress distribution, hence it is important to understand the latter. To determine the shear stress distribution, we start with the equation of equilibrium applied to a cylindrical control volume that is oriented coaxially with the pipe as shown below. So here we assume that we have a pipe here. So and then because the pipe is circular, so we take our control volume like this one. So this is our control volume. Okay. So normally in Poiseuille flow, because we are so it will reflect the flow in pipe. So normally we assume that the flow is from bottom to the top like this. So means so because normally in flow in pipe, this is the pressure. There are no atmospheric pressure, so the pressure will be developed. There are a hydraulic pressure actually. The pressure developed in inside that flow. So that's why normally we use Bernoulli equation. If you remember, the simple one is a flow in pipe. So we calculate the pressure using Bernoulli equation. Then we could solve the problem. So we have this control volume. So and then again we assume that the pressure developed on this side will push to this surface, and then the pressure at this side will push to the surface. So when pressure acts on certain surface, so it will give us force. So and then again when shear stress occur, so you know that if the flow is in this direction, so we will have resistance from the molecule at this direction. So this resistance is actually caused by the shear stress. So when shear stress acts on the surface, so we multiply with the shear stress, so it will create another force here. So we have the force is equal to P times A. So and then we have another force created by the shear stress. So in my handwriting, normally I will use F as the force. So in textbook, maybe they use P. Sometimes they use capital P for force and small p for pressure. So I don't want to use P because it's easy to misunderstanding whether it is pressure or force. Okay. So I think you are familiar with this one. And then here, the A here. So the A here can be written as 2 pi r times L. So in this situation, the L here is actually the delta S here. So and then another thing, so for sure the gravitational effect, the gravity pull this element, and then we could get the weight, the weight is force, and then the weight element for the z for the s axis here can be written is weight times sine alpha. So I think you could read all of these symbol here. So because we will use polar coordinate, so means that we need to take care about the radius. So this is the radius. Normally we take capital R as the maximum radius. So for the condition above, it is assumed that the flow is uniform, streamlines are straight and parallel, therefore the net momentum flow through the control volume is zero. Also, the pressure across any section of the pipe will be hydrostatically distributed. Thus, the pressure force acting on an end face of the fluid element will be the product of the pressure at the center of the element, also at the center of the pipe and the area of the face of the element. With a steady uniform flow, equilibrium between the pressure, gravity, and shearing force acting on the fluid will prevail. Consequently, the momentum equation yield the following. So we assume that in equilibrium, the total force is equal to zero. Then we could write as this one. So this PA is the pressure from bottom to the top. So this is another pressure. So I think we have this pressure and this direction pressure. So and then our weight is at this direction and our stress, shear stress is at this direction. That's why we have the negative sign here. So we have the negative sign here and we have another negative sign for this one. And then it is equal to 0 because this is in the equilibrium. So and then the weight here, W is weight, so it is equal to mg. Okay, and then mg is equal to rho, and m is rho and volume, and then we have a g here. So and then rho and g, okay, and then we have the volume. So the volume here means the cross-sectional area A times the L times the length. So the length is delta S. So the rho and g here can be simplified as gamma, because normally in fluid mechanics we will use gamma as rho and g. Okay. So and the sine alpha can be written as dz ds. So I think you could see the diagram here. Okay. So and then we substitute into the equation. So we have equation 1 here. So we substitute everything. We simplified all this thing because if you get this, so we could cancel the value of PA actually. So we get all of this. So and then we divide with delta S and A. So we could obtain the value of tau is equal to R over 2 negative d ds p plus rho z. So see the gradient itself, ds p plus rho z is negative and constant across the section of uniform flow. It follows that d ds p plus rho z, gamma z will be positive and constant across the pipe section. So and then the tau in equation 3 will be 0 at the center of the pipe and will increase linearly to a maximum at the pipe wall. So, and then we will use equation 3 in the following section to derive the velocity distribution for laminar flow. So this is actually the basic equation that we need for the next calculation.